We now introduce bending into our strain energy explorations, and of course this only applies to linear elastic beam bending. And the key here is that we're talking about circular arc segments defined by a radius of curvature rho or a curvature kappa, which is 1 over rho. So we have the first case where we have constant bending, no shear, so the two m's are equal to each other. And what we can find is that kappa times L is equal to mL over EI. Kappa is m over EI. And that's our expression that we learned way back in our mechanics classes. If the m is slowly applied from 0 until a final value, then theta is also proportionally increasing from 0 to a final value. And our strain energy here is the area under the curve, 1/2 the base times the height. So now we can express this u in terms of m's or in terms of theta. So let's do it in terms of m's first of all. If theta is ml over EI, then I have 1/2 m times ml over EI. Or if m is equal to theta EI over L, then I have 1/2 theta EI over L times theta. So I can express it in two different ways, which is perhaps obvious if you think about the complementary strain energy. Okay, next. We have a situation now that's different from the first situation where we had constant m. Now we have varying m. So the two m's are not the same on either side of a segment. We have an incremental angle called d theta, and the length of that little segment is dx. So now d theta is kappa times dx. Instead of kappa times L, it's kappa times dx. And we know that that's still 1 over rho. We have that segment in here, and that's d squared v dx squared is our kappa, second derivative of displacement with respect to x. So we can do it a couple of different ways here. We can say that d theta is d squared v dx squared times dx, and this is the first equation for bending strain energy. So we have m squared over 2EI, which is, kind of like exactly what I did here, except now I have a dx, so I'm integrating over all the dx's, and previously I had just an L. Or I can express it as EI over 2, which is what I tried to do here, times our rotation squared. So both of these equations are showed up in the book. 6.36 is in terms of M, and 6.3-9 is in terms of displacement. Okay, just a little quick introduction to shear effects. I'm usually going to ignore the shear effects, but sometimes we'll talk about it. So let's just look at the situation of pure shear. So we have a distortion of our cantilever beam. It moves through some angle theta, and the displacement here is V sub S, S meaning for shear, of course. So we can say that V sub S is approximately theta S times L, small angles here. So the tangent and the sine are the same as theta. And that is approximately equal to our gamma xy times L, where we're going to use gamma average.